This is my fifth and last video in my module on the binomial probability distribution, in which we're actually going to extend it to include what we refer to as the multinomial distribution. Recall that the binomial probability distribution, anything that we consider to be a binomial experiment, can be reduced down to like one of two possibilities, like one or the other. So we, could think about like flipping a coin, heads or tails, or gender of a child, is a boy or a girl. Basically, we can boil it down to what we refer to as like a success or a failure. Okay, anything can be divided into two separate spaces. There are certain instances. So, for example, if we gave a survey and asked, do people approve or disapprove or have no opinion on something? Certain instances where it's not so binomial. There is more than just two sets of outcomes. Okay, so we would refer to such instances as being multinomial in nature. So that's a good example. If we gave a survey, do you approve or do you disapprove, or do you have no opinion? Or for instance, if we were to, plan a party and say, well, what does everybody want to do? It's not just movie or dinner, but maybe movie, dinner, baseball game, go bowling, something like that. Basically, we could calculate probabilities in multinomial instances much the same way that we do with binomial instances. So what we're going to do, you notice that I put in the formula for a binomial case right next door to the formula for a multinomial case, okay? And so in order to kind of lead into the multinomial case, we're going to review what we mean in a binomial instance. We say in an experiment where there are n trials and x successes, we say the probability of getting x successes is given by this. The number of trials on top, factorial, over number of successes, factorial, number of failures, factorial. And then over here we say P and Q represent the probability of success and the probability of failure respectively, where X, again, remember X is the number of successes. So basically, the probability of success to the power of number of successes times the probability of failure to the power of number of failures for this probability experiment. This formula is very, very similar to what we see for a multinomial instance. So let's take a look at this. It says if X here, it consists of these different events. So event 1, 2, 3, so on and so forth out to, let's say, the kth event. We have corresponding probabilities for all these events of success here. So we say P1 is the probability of success for this first event, P2 is the probability of success for this second event, P3 for the third event, and PK for the kth event respectively. And we say X1 is the number of times E1 will happen, so number of successes for the first event. X2 is the number of successes for the second event. X3 for the number of successes for the third event, out to xk. The probability that we get this here would be this probability of, say, x1, x2, x3, all these things. It would basically, excuse me, be the number of total trials still. So we still have the number of total trials overall, but we say we'll take the number of successes for each individual event, okay, on the bottom, factorial. So just kind of like what we did over here, we say number of successes, number of failures. Well, this time we have number of successes for each individual thing. And then we have times all of these probabilities, okay? So what I want us to recognize here is this P1 is the probability that event 1 actually is successful, times now, or to the power of X1, which is the number of successes for that given event. And P2, which is the probability of success for the second event, is being taken to the power of number of successes for that event. Basically, what I want to point out is this: all of these factorial factors down here, these are the exponents for each individual probability of success. Okay, so basically we transplanted all these numbers up over here. If I can draw an arrow to save my life here, here's an arrow. Let's do that. There we go. That's better. But basically, we just transplanted them up here. And so, as we work through this first example, you'll kind of see what I'm talking about. But we'll keep things in the order that they need to be. So we say, all right, in a large city, 50% of the people choose a movie, 30% choose dinner and a play, and 20% go shopping as a leisure activity. So we say if a sample of 5 people is randomly selected, so we have a sample size here, 5 people randomly selected, find the probability that 3 are planning to go to a movie, 1 go to a play, and 1 go to the mall. So let's go ahead and start with this. We don't have to define success or failure here. As a matter of fact, what we need to do is essentially just go through all the different possibilities. So we have a play, shopping. Oops, let's go in order. I'm reading the problem here out of order. We say movie is our first event, movie. Then go to a play, could be another thing, or go shopping, okay? And we have the probabilities of success for all of these. So probability of success going to a movie is 50%, so we say 50% often go to a movie. 30% go to a play, and 20% go shopping. Okay, so we have the probabilities of success for each individual event. Now we're going to look at the probability down here. So if I had to write out this probability, it's not very fun to write out, but we say the probability that we have this. Find the probability that 3 go to a movie, comma, 1 goes to a play, comma, and then 1 goes shopping to the mall. Okay, so this is the probability we want to find. The thing I want to point out here is this. We have a sample of size 5. So this is very, very much like the binomial probability distribution, in that when we write this out, here's what we're going to start with, this weird expression out front, in which we have, first of all, this all equals, we'll switch colors here, this all equals the size of the sample, or the number of trials for our experiment, factorial, over this, and we're just going to drop in each of these respectively. We say this is like our x1, our x2, and our x3 here. We get 3 factorial times 1 factorial times 1 factorial. And you'll notice that all these numbers down here, they add up to be the total number of things in our sample in the first place. And as far as what goes out over here on the right, we'll just drop in their probabilities of being successful. So for a movie, we say it's a 50% probability. For going to a play is 30% probability. And then going shopping is a 20% probability. And like we said up top, like I said up top, we're just going to drop in the exponents as they need to go in. So this is the expression we need to evaluate here. The unfortunate thing is we have no table to evaluate this with. That is, we have a table of already established calculated figures for binomial probability distribution. We don't have that here, so we're just going to actually have to calculate this. So our 1 factorials, those are 1. They drop out. So if we were to reduce this here, we get 5 times 4 times 3 factorial over 3 factorial, where our 3 factorial is gone. And then times all of these. So 0.50 to the third, 0.30 to the first. I'm just going to leave that out then. Since it's to the first power, I don't need to write that. Times 0.20 to also to the first. So we get our calculator out here. We say, all right, we've got, let's see, 5 times 4, which is 20, times, now I'm going to put in parentheses, 0.5 to the power of 3 in parentheses. So multiplying those, we get 20 times 0.5 to the third is 2.5. Now that times 0.3 equals times 0.2 equals. So we get 0.15. So the probability that this actually occurs is about a 15% chance. Okay? And so that's how the multinomial kind of unfolds. So we're going to look at one more example here and we'll be done with this one. It says, in a music store, a manager found that the probabilities of a person buying 0, 1, or 2 or more CDs are 30%, 60%, and 10% respectively. So these are our probabilities of, say, quote-unquote success. So we say if 6 customers enter the store, so this is our M, this is our sample size, find the probability that 1 won't buy any CDs, so 1 buys none, 3 buy 1 CD, and 2 buy 2 or more CDs. Okay, so to write this out, we say probability, we would say 1 that buys none, we have 3 that buy 1, and then 2 that buy 2 or more. So this is the probability we want to find. So let's go ahead and start with a few simple things here, starting with this. The size of our sample. Let me move this a little bit left. Size of our sample is we had 6 people, so 6 factorial, and then we'll just drop these values in down here. We say 1 factorial for the no CD case. We say 3 factorial for the buying exactly 1 case, and then 2 factorial for buying 2 or more. And then we'll just drop in our probabilities over here respectively, and then fill in what we need in terms of our powers. So here's what I know. We say the probabilities of success, we say 0.3 or 30% will buy no CDs, 60% will buy exactly 1, and then we have the other 10% buying 2 or more. And then again, we can just drop these numbers up here and then evaluate this expression. So I don't know, working this one out here, we say 6 times 5 times 4 times 3 factorial over, now I'm going to drop out my 1 factorial. We have 3 factorial, 2 factorial, where 3's cancel out. Of course, 2 factorial, which is 2 times 1, is just 2, so we'll ignore this for now. And we say we'll just put the rest of this stuff in the calculator. So 0.3 to the first is 0.3, 0.6 to the third, we're actually going to need to evaluate that here. And then we have 1/10 or 0.1 to the second. So getting out the calculator again here, let's go ahead and pull this over here. We have this. We have 6 times 5 times 4. So the top of this is 120. And now we need to divide that by 2. So we say divided by 2. So the expression out front is 60. It's now 60 times 0.3. So times 0.3 equals 18. Now we're going to take that times 0.6 to the third. So times, in parentheses, 0.6 to the power of 3 in parenthesis, enter. And then we say, okay, now take that times, in parentheses, now 0.1 squared. So 0.1 to the power of 2 in parenthesis equals. So we get about a 3.888% chance. So 0.303888. So the likelihood of this occurring exactly as we have it listed, theoretically, we have one person not buying any and 3 people buying 1 CD and 2 people buying 2 or more in a sample of 6 people, is only about a 3.88% chance. But that is how you would use the multinomial distribution and how it is related to the binomial distribution. Cheers.